Swing is the primary Java GUI widget toolkit. It is part of Oracle's Java Foundation class as an API for providing a graphical user interface for Java programs. Swing was developed to provide a more sophisticated set of GUI components than the earlier Abstract Window Toolkit. Swing provides a native look and feel that emulates the look and feel of several platforms, and also supports a pluggable look and feel that allows applications to have a look and feel unrelated to the underlying platform. It has more powerful and flexible components than AWT. In addition to familiar components such as buttons, checkboxes and labels, Swing provides several advanced components such as tabbed panel, scroll panes, trees, tables, and lists. Unlike AWT components, Swing components are not implemented by platform-specific code. Instead, they are written entirely in Java and therefore are platform-independent. The term lightweight is used to describe such an element. History: the Internet Foundation classes were a graphics library for Java originally developed by Netscape Communications Corporation and first released on December 16, 1996. On April 2, 1997, Sun Microsystems and Netscape Communications Corporation announced their intention to incorporate IFC with other technologies to form the Java Foundation classes. The Java Foundation classes were later renamed Swing. Swing introduced a mechanism that allowed the look and feel of every component in an application to be altered without making substantial changes to the application code. The introduction of support for a pluggable look and feel allows Swing components to emulate the appearance of native components while still retaining the benefits of platform independence. Originally distributed as a separately downloadable library, Swing has been included as part of the Java Standard Edition since Release 1.2. The Swing classes and components are contained in the JavaX Swing package hierarchy. Architecture: Swing is a platform-independent, model view controller GUI framework for Java, which follows a single-threaded programming model. Additionally, this framework provides a layer of abstraction between the code structure and graphic presentation of a Swing-based GUI. Foundations: Swing is platform-independent because it is completely written in Java. Complete documentation for all Swing classes can be found in the Java API Guide. Extensible: Swing is a highly modular-based architecture, which allows for the plugging of various custom implementations of specified framework interfaces. Users can provide their own custom implementation of these components to override the default implementations using Java's inheritance mechanism. Swing is a component-based framework, whose components are all ultimately derived from the JavaX Swing component class. Swing objects asynchronously fire events, have bound properties, and respond to a documented set of methods specific to the component. Swing components are JavaBeans components, compliant with the JavaBeans component architecture specifications. Customizable: given the programmatic rendering model of the Swing framework, fine control over the details of rendering of a component is possible. As a general pattern, the visual representation of a Swing component is a composition of a standard set of elements, such as a border, inset, decorations, and other properties. Typically, users will programmatically customize a standard Swing component by assigning specific borders, colors, backgrounds, opacities, etc. The core component will then use these properties to render itself. However, it is also completely possible to create unique GUI controls with highly customized visual representation. Configurable: Swing's heavy reliance on runtime mechanisms and indirect composition patterns allows it to respond at runtime to fundamental changes in its settings. For example, a Swing-based application is capable of hot-swapping its user interface during runtime. Furthermore, users can provide their own look and feel implementation, which allows for uniform changes in the look and feel of existing Swing applications without any programmatic change to the application code. Lightweight UI: Swing's high level of flexibility is reflected in its inherent ability to override the native host operating system's GUI controls for displaying itself. Swing paints its controls using the Java 2D APIs, rather than calling a native user interface toolkit. Thus, A Swing component does not have a corresponding native OS GUI component, and is free to render itself in any way that is possible with the underlying graphics GUIs. However, at its core, every Swing component relies on an AWT container, since component extends container. This allows Swing to plug into the host OS's GUI management framework, including the crucial device screen mappings and user interactions, such as key presses or mouse movements. Swing simply transposes its own semantics over the underlying components. So, for example, every Swing component paints its rendition on the graphic device in response to a call to component paint, which is defined in container. But unlike AWT components, which delegated the painting to their OS native heavyweight widget, Swing components are responsible for their own rendering. This transposition and decoupling is not merely visual, and extends to Swing's management and application of its own OS-independent semantics for events fired within its component containment hierarchies. Generally speaking, the Swing architecture delegates the task of mapping the various flavors of OS GUI semantics onto a simple, but generalized, pattern to the AWT container. Building on that generalized platform, it establishes its own rich and complex GUI semantics in the form of the component model. Loosely coupled and MVC, the Swing library makes heavy use of the model controller software design pattern, which conceptually decouples the data being viewed from the user interface controls through which it is viewed. Because of this, most Swing components have associated models, and the programmers can use various default implementations or provide their own. The framework provides default implementations of model interfaces for all of its concrete components. The typical use of the Swing framework does not require the creation of custom models, as the framework provides a set of default implementations that are transparently, by default, associated with the corresponding component child class in the Swing library. In general, only complex components, such as tables, trees and sometimes lists, may require the custom model implementations around the application-specific data structures. To get a good sense of the potential that the Swing architecture makes possible, consider the hypothetical situation where custom models for tables and lists are wrappers over DAO and/or EJB services. Typically, Swing component model objects are responsible for providing a concise interface defining events fired, and accessible properties for the data model for use by the associated component. Given that the overall MVC pattern is a loosely coupled collaborative object relationship pattern, the model provides the programmatic means for attaching event listeners to the data model object. Typically, these events are model-centric and are mapped by the component specialization into a meaningful event for the GUI component. For example, the JTABLE has a model called Table Model that describes an interface for how a table would access tabular data. A default implementation of this operates on a two-dimensional array. The view component of a Swing component is the object used to graphically represent the conceptual GUI control. A distinction of Swing, as a GUI framework, is in its reliance on programmatically rendered GUI controls. Prior to Java 6 Update 10, this distinction was a source of complications when mixing AWT controls, which use native controls, with Swing controls in a GUI. Finally, in terms of visual composition and management, Swing favors relative layouts as opposed to absolute layouts. This bias towards fluid visual ordering is due to its origins in the applet operating environment that framed the design and development of the original Java GUI toolkit. Relationship to AWT. Since early versions of Java, a portion of the Abstract Window Toolkit has provided platform-independent APIs for user interface components. In AWT, each component is rendered and controlled by a native peer component specific to the underlying windowing system. By contrast, Swing components are often described as lightweight because they do not require allocation of native resources in the operating system's windowing toolkit. The AWT components are referred to as heavyweight components. Much of the Swing API is generally a complementary extension of the AWT rather than a direct replacement. In fact, Every Swing lightweight interface ultimately exists within an AWT heavyweight component because all of the top-level components in Swing extend an AWT top-level container. Prior to Java 6 Update 10, the use of both lightweight and heavyweight components within the same window was generally discouraged due to Z-order incompatibilities. However, later versions of Java have fixed these issues, and both Swing and AWT components can now be used in one GUI without Z-order issues. The core rendering functionality used by Swing to draw its lightweight components is provided by Java 2D, another part of JFC. Relationship to SWT, the standard widget toolkit is a competing toolkit originally developed by IBM and now maintained by the Eclipse community. SWT's implementation has more in common with the heavyweight components of AWT. This confers benefits such as more accurate fidelity with the underlying native windowing toolkit, at the cost of an increased exposure to the native platform in the programming model. There has been significant debate and speculation about the performance of SWT versus Swing. Some hinted that SWT's heavy dependence on JNI would make it slower when the GUI component and Java need to communicate data, but faster at rendering when the data model has been loaded into the GUI, but this has not been confirmed either way. A fairly thorough set of benchmarks in 2005 concluded that neither Swing nor SWT clearly outperformed the other in the general case. Examples, a basic example. The following is a rather simple Swing-based program. It displays a window containing a label and a button. Notice how all instantiation and handling of Swing components are done by creating an instance of the class, which is subclassed from the runnable class. This is then run on the event dispatch thread by use of the method Swing utilities invoked later, runnable, created in the main method. Although Swing code can be run without using this technique, it is considered to be good form, as Swing is not thread-safe, meaning that invoking resources from multiple threads can result in thread interference and memory consistency errors. See also, Swing Labs are Euro extensions to Swing that might be included in Swing in the future. Standard Widget Toolkit, a third-party widget toolkit maintained by the Eclipse Foundation. JavaFX, a software platform for creating and delivering rich Internet applications that can run across a wide variety of devices, which is intended to be the successor to Swing. Notes. References. External links, Java SE7, The Swing Architecture.